So now we're going to look at a discussion on homogeneous versus non-homogeneous differential equations. So when we talk about something that is homogeneous, we're talking about all the y stuff on the left, and it's going to be equal to 0. So we could think about that g of x function as being 0. If it's non-homogeneous, all the y stuff's on the left, we have some function that's not 0 on the right. We say g of x is not identically 0. And what that means is that it's just not equal to 0 always. Could be a place where it is equal to 0 sometimes. Like this could be the function y equals x, right? So if g of x is x, x is equal to 0 is 0, but it's not identically 0, which means it's not 0 all the time. And we said that that's non-homogeneous. So different instructors say different things. I had an instructor back in college that called this homogeneous and non-homogeneous. Most of my instructors, when I had courses that dealt with equations like this, used homogeneous and non-homogeneous. So that's the terminology I use because that's what 9 out of 10 of my instructors used. So if you watch different YouTube videos, they may pronounce it differently. So it's like tomato versus tomato, I guess. I don't know. Anyway, so how do we solve something like that? If we have a function that looks like this, or a differential equation that looks like this is homogeneous because it's equal to 0. But if we change it to look like this, now we have something that's non-homogeneous. So it turns out that the way we solve for a non-homogeneous differential equation is that we first turn it into a homogeneous differential equation by solving what we call the associated homogeneous differential equation. So we have this x cubed y triple prime plus 6y prime plus 10y is equal to e to the x. So that's what we want to solve. You would start out by solving the associated homogeneous differential equation. That would be our associated homogeneous differential equation. Since it's third order, you will have 3 different solutions to that differential equation. If you have a second order, you will have 2 solutions. If you have a fourth order, you will have 4 solutions. So you'll have 3 solutions to that guy, and then you've got to figure out what to do with that non-homogeneous part. And there are techniques that we will talk about in this chapter to help us solve something like that. But that's essentially what happens. So then what happens is we take all those pieces and we're going to put them together using something called the superposition principle. So the superposition principle just says that if you have k solutions for an nth order homogeneous, so let's say we have a second order, and that means we're going to have 2 solutions. Then we can put them together. I'll call them y1 and y2. So our final solution for this would be c1 times y1 plus c2 times y2. So always some constant of integration multiplied by each of those solutions. And it's the sum of all of those. If we had a third order, we would have 3 of these. So then we would add that third solution to it. If we had third order. Fourth order, we would add a fourth one and so on. So if we look at example 4, they're telling us that they have 2 solutions. Of this differential equation. Okay, now notice this is the third order, but they've only found 2 of the 3 solutions. So you could verify that this satisfies this, and you can verify that this solution satisfies that differential equation also. And the superposition principle also guarantees that the sum of those 2 would satisfy that differential equation as well. So we could say that the superposition of those 2, which would be y equals c1 x squared plus c2 x squared ln of x. This is your c1 y1 plus c2 y2. That would satisfy that differential equation as well. So it's also got to be a solution for that. So I just want to go back up and touch on this corollary to that theorem. So we said that y1 was a solution. Here we're saying that x squared is a solution to this. That also means if I multiply that solution by any constant, then that's also going to be a solution for that differential equation. So in this case, if we look at example 4, then c1x squared would also satisfy that differential equation. I believe I circled the wrong thing earlier. Likewise, b, we have a homogeneous linear differential equation. If this guy is equal to 0, then that means that the trivial solution is always going to satisfy that differential equation. Because if I take derivatives, depending on how many I need, in this case I need 3, the derivative of 0 is always 0. And if I substitute that in, I'm going to get 0. So those are a couple of things just to keep in mind as we go through this theory. So that superposition principle is actually creating a solution that's the sum of it's a linear combination of linearly independent functions. So let's look at what the definition of linear independence means. So let's say we have a set of functions. We say that they are dependent on an interval if there exist constants that are not all 0, such that this guy is going to be a true statement. So we're saying that these could be different numbers, but they're not necessarily going to be zeros. If they are all zeros, then they are independent, which means the only way that you could form that combination here and get 0 would be if all of these are going to be equal to zeros. So this is going to go back, if you've taken linear algebra, to finding something called the Wronskian. That's the easy way to check for functions and linear independence among functions. So what we want is this solution where we are adding all of these functions together. We want each of those functions to be linearly independent. We don't want anything where I can take the first two functions, add them together, and get the third function. We want to, and what that does is it simplifies what that solution is going to be, and that's what gives it a better, what's the word I'm looking for here? A simpler look in math. We don't want to duplicate efforts. We want to write our solution as simply as possible. So eliminating linear combinations is the best way to do that. And that's why we look for that linear independence among the solutions. So that's where the idea of that Wronskian is going to come in. So just to kind of review what a Wronskian is. Let's say you're checking for linear independence. Let's say we were asking, are the functions x and e to the x linearly independent? When we look at the Wronskian, we put our functions across the top, and then we take derivatives. So the derivative of x is 1, the derivative of e to the x is e to the x. And then we find what's called the determinant. So to find the determinant of a 2 by 2, it's going to be x times e to the x minus 1 times e to the x. And we're asking, does that give us 0? Well, x e to the x minus e to the x is not 0. If it's not 0, then we say they are linearly independent. Now, I also got a different example. So what if we're looking at x squared and negative 3x squared, and we're asking, are they linearly independent? Well, we would say these guys are not. They are dependent. Okay, because I could get this guy just by multiplying this by negative 3, which means that this is a combination of that. It's actually a scalar multiple of that one. That's what it means to be dependent, is that you can write one function in terms of the other functions as linear combinations. But let's show it using the Wronskian. So I'm going to put my x squared and my negative 3x squared across the top. And then I'm going to take the derivative of x squared, which is 2x. Take the derivative of negative 3x squared, which is negative 6x. And then we're going to multiply. So it's these two. So that's a negative 6x cubed minus these two, which is negative 6x cubed. And we know that gives us 0. If the Wronskian gives you 0, then they are dependent. If the Wronskian is not 0, then the functions, and I'm going to use FUN for functions here. Let me clean that up a little bit. Are independent. So it's as simple as that. If we had 3 functions, we would do the same thing. We would go across the top with function 1, function 2, function 3, and then we would take derivatives. And we would have to take up to the second derivative and then find the determinant of that. We'll do more with the Wronskian as we go through chapter 4, but that's just a brief introduction about linear independence. You can see how these courses, once you start getting to this level, they start to intertwine with each other. We're going to actually see a few more linear algebra elements as we proceed through differential equations. So it's kind of cool to see all of those courses starting to connect together at this point. So if we look at example 5, here is a solution. We're asking, are those actually dependent functions? And the answer is that they are dependent. They are not independent. And this has to go back to trig. So we could go through the Wronskian and we could show that this one's going to be, this one would be extremely fun because we would have a 4 by 4 that we would have to take the determinant of. So instead of going through that, which can be a little tedious, let's use a little logic on this. We know that to have independent functions, we cannot write one as a combination of the other ones. Is there a way you could write this in terms of another function? And the answer is yes. We could write sine squared in terms of cosine squared because we know that there is a Pythagorean identity that connects those two. And that Pythagorean theorem, Pythagorean identity, is cosine squared plus sine squared is equal to 1. So if we rewrite that, then we could say sine squared is equal to 1 minus cosine squared. So this can be written as that it's got a cosine. So those are not independent. We could do the same kind of thing with this, tweak it, so that we could write tangent in terms of secant, and then we would have things written in terms of cosine, secant, and then a constant 1. So we actually don't need all 4 of those functions. We could condense that down even more. Those are actually dependent functions. And we went through that without having to do that Wronskian, but we could certainly do the Wronskian and prove that. The same thing is going to be true in example 6. They're given us 4 functions here. And we could actually write the second one as a linear combination of the other ones. If we were to take 1 times that first function, which is square root of x plus 5, plus 5 times that third function, and then 0 times the fourth function. And you can see how that's going to give us that f2 function, square root of x plus 5x. So we're able to write f2 as a linear combination of all of the other ones, which means f2 is dependent on f1, f3, and f4. So those are actually dependent functions. If we were to find the Wronskian for that one, then we would end up with still another 4x4. That would be a tedious process. But we would end up with 0 at the end of that. So I would not ask you to find the Wronskian of a 4x4 in class, just because that can get tedious. But I do expect you to be able to look at these and start questioning the idea of whether or not they are dependent. We talked about the idea of the Wronskian, and that's the best way to determine whether or not we have a set of linearly independent functions. That's always the goal. So we said that as long as that Wronskian is equal to 0, then they are dependent. If it's not 0, then they are independent. And that's our goal. That's what we're looking for there. So as long as we have independent solutions, then we call those the fundamental set of solutions for this nth order differential equation. So then the general solution of the equation is going to be using that superposition principle where we're putting them all together. It's the sum of a constant times the first solution plus a constant times the second solution, and so on. So just to kind of look at an example, we have y1 and y2. So if we look at the Wronskian there, now, we can tell just by inspection, just by looking at this, that there's no way I could get this guy from this just by multiplying it by something. They are not combinations of each other, but we can verify with the Wronskian. So we would put those in that first line, and then you take the derivatives in the second line. So then when we find the determinant of a 2 by 2, it's always a times d minus b times c. So it's going to be this, which would be negative 3 times e to the 0 minus this, which would be 3 times e to the 0. And that's going to give us that negative 6 that they got there. So since we got something that is not 0, then we conclude that they are independent. And since they're independent, then we can put them together using that superposition principle and form that general solution for that differential equation, which was here. So what we're saying in example 8 is that this is also a solution of that differential equation from the previous example. But in order for us to get that, it's got to be a combination of the solutions above. So we can tweak this any way we want to find additional solutions. Notice this doesn't have any constants of integration in it, which means it's probably a particular solution given some kind of initial conditions. We don't have those initial conditions. They're not asking us to solve that here. They're just trying to prove a point that this is equivalent to a linear combination of that. So if we were to kind of break that apart, we would be able to rewrite that sinh hyperbolic sign in terms of that. So it would be a linear combination. And then you could obviously put these two pieces together. Don't forget to multiply that by that 4. So you can see how it's a combination of e to the 3x's and e to the negative 3x's. In this example, we have 3 other solutions that satisfies this differential equation. Okay, notice this is a homogeneous third order differential equation, and they gave us all 3 solutions. They're asking us to verify that they are linearly independent. That's why they're using the Wronskian here. So we write the functions across the top, then we take derivatives. The derivative of e to the x is just e to the x. The derivative of e to the x is 2e to the 2x. And the derivative of that is 4e to the 2x. And then we take the two derivatives of e to the 3x, and then we find the determinant. So just to kind of review, finding determinants of a 3 by 3. This is something you saw back in probably 172, a trig class. The easy way to do that is to recopy the first 2 columns. This is a shortcut method. This works for a 3 by 3. It does not work for anything else. It's just a shortcut for a 3 by 3. The other option is row expansion, which we talked about in linear algebra. And then you multiply down the columns, down the diagonals. So we're going to have 18e to the 6x. Multiply here, plus 3e to the 6x, and then multiply here, plus 4e to the 6x, and then we're going to subtract, and then we're going to go the other way. So this is going to be a 9e to the 6x, 12e to the 6x, and 2e to the 6x. When you're doing this, be careful and make sure you line up those diagonals. Otherwise, it can cause a mess. So 18 plus 7 is 25. And then we have 9 plus 12 plus 2. So 14 plus 9 is 23. And that gives us a 2e to the 6x. And we know that that's not equal to 0, which means that they are independent. And since they're independent, then we can put those together to form the general solution for the homogeneous differential equation using that superposition principle. So it would look like that. So what if we have a non-homogeneous differential equation? We already said we had to solve the associated homogeneous differential equation. So we would do that. But then we have to find the solution to the non-homogeneous part. And that's called the particular solution for that. So when we form that general solution, we're going to have that solution to the the solution to the associated homogeneous differential equation. Notice each one of those is multiplied by a constant. And then we're going to add that particular solution on the end. Notice that that is not multiplied by a constant. That's important. It will not be. It's very specific to that particular problem. And we call that the complementary solution when we put that piece together. So this is the complementary plus the particular piece. So now that we've talked about all the theory that's involved, we're going to put this into practice when we solve these differential equations, starting with this chapter and the next section, which is reduction of order.